This is day 24, lecture 24. Today we're going to do the last section in the text prior to our test in here. It's section 2.10. We have accumulated a group of facts relative to the first derivative, so we're going to kind of see what we know about the function based on that accumulation of first derivative facts. We have a smaller but yet a growing accumulation of facts about the second derivative. So we want to see what that group of facts will tell us about the original function. So that's really kind of the task at hand. I don't think there'll be anything new today. It may be a different way of looking at it. We're just going to try to put all the first derivative information together and the second derivative information together and see what we can determine about the function from that information. So let's look at these things actually one at a time, because I want to do some things diagrammatically with this before we advance from the first to the second. But the first part of this, what does f prime say about f? And this isn't a complete list, because I think we actually know more, but let's just start with this and see what it tells us. If the first derivative is greater than 0, so it's positive on some interval, then the function is increasing on that interval. Is that new information today? We've talked about that, right? First derivative positive. What is first derivative? Slope of the tangent. So if the slope of the tangent is positive, that means the curve is on its way up in that region. Second piece of information, if the first derivative is less than 0, it's negative, then the function is decreasing on that interval. So I hope that's not new information. Now, what are we missing? It's not a comprehensive list here. What types of situations have happened with us where it was not positive and not negative?
If the slope is 0.
The slope is 0, so if the first derivative is 0, what do we know about the function where the first derivative is 0? It has 0 slope, so tell me, is it increasing or decreasing? Really,
No,
neither
it's
one.
horizontal.
So at that instant, it's just kind of flat, right? So we've got a place where it's not increasing, it's not decreasing, it's kind of instantaneously, possibly between those regions. Or it might be increasing and then flatten out a little bit and then start to increase again. So it doesn't have to change direction where the derivative is 0. Is that a comprehensive list? What else might the derivative be? 0, positive, negative,
Infinite?
undefined. Okay? So, or does not exist. So if the derivative is undefined, we know some things that might be happening there. But let's say it's undefined because it's some situation where we've divided by 0.
It's vertical.
Vertical. We have a vertical or very steep part of the graph in that area. So as it approaches that point, it gets steeper and steeper, and at that point, it's instantaneously vertical. And then when it leaves there, it's nearly vertical. And I don't think we've examined anything else about first derivative that isn't on that list. So that's a pretty comprehensive list as far as first derivative is concerned. And we use these critical values for the first derivative. We find out where the derivative is 0, and we find out where the derivative is undefined. Then from there, we'll decide where is it positive, where is it negative, so that'll tell us what the nature of the function is. All right, we'll come back to the second derivative stuff in a minute. So let's say we have a nice, smooth, continuous function that behaves pretty well and does something like this. So if we were describing some things about the first derivative, or if we wanted to kind of analyze the first derivative, and we can go the other direction, which I'd like for us to do before class is over today, is not start with the function and go to the derivative, but start with the derivative and go to the function. Your authors address that and call that an antiderivative, which is exactly what it is. But you would probably want to figure out where's the derivative 0. There, and maybe right here. Here it looks like it flattens out, right? Maybe that's not right. Maybe right in there. The derivative is 0. Now I did that in particular because I wanted to show that the graph could increase and flatten out, and then at some point be instantaneously flat, wherever that is. And then it doesn't have to decrease from there. It could leave there and slightly increase and then pick up the rate of increase. So just because the derivative is 0, it doesn't mean we're going to have a change in direction. So you'd probably want to identify those points. Does it look like here? Do we have any places where the derivative looks like it's undefined? What would you be looking for? Some of you went right away and you said, no, there aren't any. What are you looking for?
Vertical line or
Okay, where the graph is nearly vertical,
discontinuous.
right? Or where else? What else?
Discontinuity.
Okay, it
Well,
might
there's
be
no point.
discontinuous at a point. Certainly we don't expect a derivative to exist there. Or a corner, right?
Or
Some type of corner
cusp.
or cusp where we've got an abrupt change in direction. Don't have any of those here. So this is clearly kind of a smooth curve where we don't have any places where the derivative is undefined. All right, let's take this area. Points in here, the slope of the tangent, slope of the tangent. In fact, all of that area, what's true about the slope of the tangent lines?
Increasing.
Okay, the function is increasing. What about the slope of the tangent?
Decreasing.
They're positive, right? Positively sloped. So here the function is increasing. And we can tell that because the slopes of the tangent lines are positive. Here they're getting less positive. Basically they're getting closer to 0, right? This graph is starting to flatten out. At a certain point the derivative is 0. What about the slopes of the tangent lines in this region?
negative.
Negatively sloped? And in regions where the derivative is negative, it has a negative slope. The function itself is decreasing. Now let's see if the rest of the graph that's true. Well, we don't have any more decreasing parts, but here it's increasing. Slope of the tangent is positive. Almost 0. It leaves here and it's almost 0. And then it picks up and is positive again. And the rest of that graph is increasing, right? So you should expect to kind of link those two together in such a manner that they can't be separated. First derivative positive means the function is increasing. First derivative is negative means the function itself is decreasing. And then we've already dealt with these things called the so-called critical values of the first derivative, where the graph flattens out, where the derivative is 0, and where it gets real steep because the derivative is undefined. Okay, let's take a couple of shapes of a graph here. Break them down a little bit further. So let's say a graph has this kind of a shape. That's the function. That's the f of x. Now I'm going to plot some points here and draw in some slopes. Remember, slopes are derivatives. And I want us to analyze as we move from left to right, what happened to those slopes? Well, this looks like a positive number, maybe a slope of 3, maybe a slope of 1, a slope of 1/2, a slope of 0, a slope of -1/2, maybe -1. What happened to those slopes as we progress from left to right?
Decrease.
The slopes were decreasing, right? So if the slopes are decreasing, the slopes are derivatives, when the slopes are decreasing, do you expect it to have that kind of a shape? Right? Slopes are getting less as you go. That kind of a shape is concave down. Now think about it. What must be true if the rate of change of the derivatives is negative? That means that the second derivative
Be less than 0.
would be less than 0. That's correct. So it's exactly the same relationship. If the first derivative is negative, the function is what? Decreasing. If the derivatives are negative, then the second derivative has got to be, if the derivatives are decreasing, the second derivative is negative. I'll write that down. So if the second derivative is negative, we're going to have this kind of shape because the rate of change of the derivative is negative. Isn't that a second derivative? The rate of change of the derivatives, kind of the derivative of the derivatives, must be second derivative. If that's negative, the graph is concave down. Here's what I said I would write down. So we had this, where the derivative was negative, the function was decreasing. Now I'll just put a little extra prime mark in each side. Now if the second derivative is negative, the derivatives are decreasing. Very similar statement. I just put an extra derivative mark on each side. So this is the one that we want to spend a few moments on now, that if the second derivative is negative, the derivatives are decreasing, and if the derivatives are decreasing, it's got that kind of shape, that concave down kind of a shape. Okay, I'm going to move that one. Any question about that one? And let's take the other shape where the derivatives are increasing. If you just think about what I just said, in order for the derivatives to increase, doesn't this have to happen? That kind of a shape? Look at the slopes from left to right. Here's a fairly steep negative slope, a little less steep than that, but still negative. Somewhere in here the derivative is 0. Then we have small positive numbers. Then we have larger positive numbers. So from left to right, what happened to the derivatives? They were increasing. So the derivatives were increasing. And if the derivatives are increasing, that's the rate of change of the derivative is positive. That means that the second derivative is positive. So if the rate of change of the derivative, which is second derivative, is positive, that means the curve has to have that shape, which is concave up. So second derivative, what will second derivative tell us about the function? It's going to maybe not quite as informative as far as increasing and decreasing, a little more subtlety to the what's going on in the graph. It'll kind of tell us how it's increasing and how it's decreasing, in a sense that how the curve is flowing from left to right. Is it concave up or concave down? So a quick summary, second derivative, positive. What's that tell us about the function?
It's increasing.
Tells us the function is concave up. Tells us the derivative is increasing. I'm just kind of skipping that derivative. What's the second derivative? If it's negative, what's that tell us about the original function? Concave down. Now we haven't addressed second derivative equal to 0 or second derivative undefined, which we're about to, but let's get the kind of the major points out of the way first. Back to my original sheet. second part of this, what does f double prime say about f? And if you just wrote down what I had up there, you don't have to write it down again, because here it is again. If the second derivative is positive, the function is concave up on that interval. If the second derivative is negative, the function is concave down on that interval. We'll still want to find out where the second derivative is 0. That'll be helpful. Now, if you think about it, it's not concave up at that point. It's not concave down. So maybe it's in transition from being concave up to concave down. That's a possibility. We'll also want to find out where the second derivative is undefined. And once again, it might be in transition from being concave up to concave down, or vice versa. So these two places, we'll call those potential points of, what's that other word I'm going to write down? Anybody heard that before? Points of inflection. Now, I put potential there because they may or may not be. It actually has to change concavity there in order to be a point of inflection. Let me give you some examples of where a second derivative, what it might look like, where a second derivative is 0. Okay, nice, smooth, continuous function. Pretty obviously, we can tell where the first derivative is 0, where the first derivative is positive, and where the first derivative is negative. That's the increasing, decreasing, flat stuff. Now let's analyze this a little bit differently. There's a point in here. I don't know exactly where it is. I'm just going to pick out that point right there. That's probably pretty close. There's a subtle transition going on this graph at that point, because this piece of the graph, would you say that would be concave down? Right? Part that I put lines on is concave down. Now, doesn't it change at that point? Somewhere in there, maybe not specifically the point that I picked out, but somewhere in there it changes, and the graph is concave up. And then somewhere in here it changes again. And then the entire rest of the graph is concave down. Is that correct? No more transitions? All of this shape right here is all concave down. So those 2 points right there would be points of inflection, where the transition occurs from being concave up to concave down. So to actually be a point of inflection, the concavity has to change there, from concave down to concave up, or vice versa. So is there a potential for a point to be a place where the second derivative is 0, but it's not a point of inflection? That potential is there. Any questions about this picture before I move this one? Okay, let me show you one where we can have a second derivative that's 0, we could have a graph that looks like this. And we could determine that at this point, right here, I know what you're thinking. You're thinking, well, there's a cusp or a corner. The first derivative doesn't exist there. That's true. There's possibility the second derivative doesn't exist there either. So whether the second derivative doesn't exist, or I'll just put undefined, or the second derivative is 0, I'm kind of grouping those together now. Those are potential points of inflection. So we will have one that looks like this. And you have to analyze, is that actually, even though it's a candidate for being a point of inflection, is it really a point of inflection? Does the graph change concavity there? It doesn't, because this piece of the graph is what?
Concave.
Concave up. And then this piece of the graph is
Concave up.
also concave up. So even though it may have been a candidate, what makes it a candidate? Because the second derivative is 0, or the second derivative is undefined. Unless it changes concavity there, it is not a point of inflection. So for this, on this picture, we don't have a point of inflection because it did not change concavity. So what's the first derivative tell us? It tells us flat, steep, increasing, decreasing. What's the second derivative tell us? Concavity, concave up, concave down, or if there's a possibility for a change in concavity. So these two derivatives can tell us quite a bit about the original function if we'll just pay attention to the details that are written about the derivatives. Okay, let me put a couple things in combination here, and you tell me what is created. Any questions about this picture before I move this one? You guys are quiet today.
Monday.
Wild weekend, huh? Just kind of get back to school so you can recover. I was never there. I was so studious when I was an undergrad. I never went out and did anything that I wasn't supposed to do.
Yes.
We believe that one.
Yeah, same.
In fact, after a lie like that, I have to look back at my notes to see where I was. I'm going to call this point right here a relative max. Sometimes it's called a local max. But in that general vicinity of the graph, a little bit left of that point, let's say over here, and a little bit right of that point, that's the highest point in that locality, in that region. So we'll call it a relative max or a local max. It might also be, when we're done graphing the whole picture, it might be the absolute max, or the global max, as sometimes it's called. But what must be true? Well, in order for this to happen, it looks like at this point, let me call this A, it looks like the first derivative is 0, right? So that makes it a candidate for a high point or a low point, or in fact neither. But what else is going on there? Tell me something about the second derivative at A.
Less.
What's that shape? What do we call that shape?
Concave down.
Concave down, so what must be true about the second
It's
derivative?
less than 0. It's negative.
Negative. Now, when you have these two in combination, will you always have a curve that's shaped like this and you have a high point? You have to, right? Because doesn't this mean concave down? And this means there's a flat place? Well, if you've got a curve that's concave down and you've located a flat place, there's got to be a high point. Those two in combination make sense with that graph? What has to happen for us to have a relative minimum?
Slope is 0 and concave up.
Okay? Call that B. So here we have a relative minimum, or a local minimum. Looks like the derivative at B is 0, and it looks like the second derivative at B is positive. So the only shape that could be is concave up, and we've got a flat place. It's got to be a low point. Must be a local minimum or relative minimum, or possibly an absolute minimum. It might be the very lowest point on the graph. So we're looking for kind of combinations of things about the derivative and second derivative that will give us some indication about what is true about the original function. Okay, let's keep moving on. I've got a couple of examples. I'm kind of skipping some examples too that I think we've already done justice to. Questions about this before I move it? Let's try this one. It's a problem in your list of exercises at the end of this section, section 2.10. Just a bunch of facts. There are a couple of facts about the function itself, a couple of facts about the derivative. Let's just see what we can determine about this picture, this f of x, from the info that's given. One of the things I like to try to do first is to pick off facts about f of x. What do we know about the function itself from this list?
At 2, it's -1.
Okay, that's a point. So we can plot a point with that.
At 0, it's 0.
So when you see the f of 2 is something, that's a point on the graph. 2, -1. Now, do we know what's going on at that point? No. It's just, here's a point. Okay, so let's take what they give us and plot it and see what happens. Okay, the f of 0 is 0. Again, we don't know anything about it at 0, 0, other than it goes through 0, 0. What else do we know about the function?
Is there a flat spot?
Well, all the other stuff looks like derivative stuff, right? Or second
The
derivative
limit.
stuff. Oh, there we go. Here's something. The limit of the function, so this is telling us about the function, is 1 as x gets tremendously large. What is that?
Asymptote.
Asymptote? Horizontal asymptote. So the y value approaches 1 as x gets huge. Okay, now I probably shouldn't put that over to the left because I don't know that that's a boundary for x approaching negative infinity. But for x approaching positive infinity, the y values are eventually going to approach 1. So that's a horizontal asymptote. At y equals 1. What else do we know about the function? The last line, this tells us something about the function. The f of negative x is the same as the f of x. That might be helpful.
Absolute.
What kind of function is that?
Absolute value.
Okay, but what category of function is that?
Is it a 1-to-1?
Think about it. The f of negative x, when I put in a -2, I get the same thing as when I put in 2.
Even.
That's even,
cool.
right? That's an even function. Gosh, you thought you could forget about that since we already got tested over that. And those are kind of handy things to hang on to.
Squared.
Now, what does that tell us?
It's symmetric.
We've got some nice symmetry going. We should have. If the f of negative x is the same as the f of x, that's why I chose this problem. This has a lot of stuff in it. Not only do we know that the f of 2 is -1, what else?
The f of -2 is negative.
The f of -2 is -1. So that gives us an additional point. Does that say what was a horizontal asymptote in this direction is also a horizontal asymptote in this direction?
Mm-hmm.
If it's got this kind of symmetry, it does. So we'll keep this thing going on out here as a boundary in both directions. Now, we haven't used anything about derivative or second derivative yet, but let's see what that says now. First derivative is negative. What's that bring to mind? First derivative negative.
It's concave down.
Nope.
Decreasing.
Decreasing, right? First derivative is increasing, decreasing, flat and steep type stuff. So first derivative negative, where? Between 0 and 2?
Mm-hmm.
Is that okay? let me try to make some notes to myself. Between 0 and 2, in this region, the graph is decreasing. Is that all right? Isn't that kind of like, well, duh, doesn't it have to decrease? How do you get from up here to down here? You have to decrease, right? So that wasn't all that helpful, but kind of backed up what we knew had to be true. I mean, there's no other way to get from this point to this point without decreasing. First derivative is positive if x is greater than 2. So any x value greater than 2. What's it doing out here? Increasing?
Mm-hmm.
Okay, anything else that we know about the first derivative?
Is it 0 at 2?
Okay, let's go back and pick this up. The first derivative at 2 is 0. I'm just going to put myself a little line segment down there, a little flat line segment to let me know that the curve gets flat. As it gets close, and then at that instant, it is in fact flat. Okay, now don't we know something else? Because of the fact that we've determined it's even and therefore symmetric.
Man.
It's got to be the same thing here, right?
Oh.
Because it's flat at those mirror image points on either side of the y-axis. Okay, anything else about first derivative? Well, can't we back this symmetry stuff up over here
Yeah.
and say, well, this is decreasing, but let's use the symmetry. You can't decrease again. How do you get from here to here? Got to increase, right? So the symmetry tells us on one side of the axis where it was decreasing, on the other side of the axis it's got to be increasing so that the two symmetric pieces match. And what? This has all got to be decreasing? Now, if you don't like that, you think it should be doing the same thing it was in the other piece, it's got to be opposite in order to be the symmetric image. Second derivative. What do we know about the second derivative? Well, we know it's negative. What's that mean? Second derivative negative.
Concave
Concave
down between
down.
0 and 1.
Between 0 and 1
And when it's greater than 4.
and greater than 4.
Uh-huh.
Okay?
Got a point of influence.
So between 0 and 1, we're concave down, and larger than 4.
Mm-hmm. 3 points.
Same thing on the other? Or are we going to go opposite? How do we make sure that they match up? Let's get the other piece here before we try to match up the symmetric pieces. First derivative is positive from 1 to 4. Excuse me, second derivative is positive, which means concave up. Is that right? Concave up between 1 and 4. I'll tell you what, let's graph what we know on the right and see how we can make on the right of the origin, see how we can make the other piece match up with the symmetry that we know it has to have. Okay, do we know how it leaves here? I'm not going to necessarily start. We know it goes through here. Do we know how it leaves here? It leaves here fairly flat.
And approaches this
And then eventually we've got to approach this dotted line. But somewhere out here, it changes concavity. So I'm
At 4.
concave up. And at 4, doesn't it have to change and
Yeah.
be concave down? Does that work? Does that match our given information? Now, where is it concave up from 1 to 4, right? So in here, I've got to have it come down and be nearly flat, then it is flat, and then it leaves there nearly flat. But at 1, it's got to change concavity and be concave down, right? So does that seem to do what the first derivative and second derivative are telling us to do with that function?
Yeah.
By the way, how many points were handed to us? Literally handed to us?
3.
Just 3, right? 2 were actually written down and the other one was given to us by symmetry. Basically, we are handed 3 points and we can figure out what this whole graph does, having been only handed 3 points. Okay, do we know what it does on the other side? Yeah, just fold it over and kind of trace it, right? It's got to leave here and be concave down, make a transition and be concave up. Continue to leave here fairly flat, continue to be concave up, and then change at this place and approach that from that side. So we should have an even function, symmetry with respect to the y-axis, and every one of those facts that were handed to us should be true. Now there's one thing that I have on this diagram that I don't necessarily know is true. And I don't know if I can sketch it without it being this way. Don't I have this graph kind of flat? Doesn't it look like I have the derivative at 0 is 0? I kind of sketched it that way. Now, does it have to be that way? It doesn't have to be that way. So I've got it getting flatter and flatter to catch that point, but that doesn't necessarily have to be true because that wasn't handed to us. I don't think it's wrong to graph it like this, but it doesn't have to look exactly like that at x equals 0. Not necessarily true, even though my sketch shows that's true. Question about this? You don't have to do it this way. You don't have to do it by the function first, the derivative second, and the second derivative third. You don't have to approach it that way, but I would get some kind of systematic approach to plotting points, you know, dealing with the increasing, decreasing, dealing with concave up, concave down. Can a function be increasing and concave up? Is that possible?
Yeah.
Mm-hmm.
Right? Increasing and concave up? That increasing and concave up? Can it be increasing and concave down?
Yeah.
One side of it, it can.
Right? Increasing and concave down. Isn't that
Mm-hmm.
increasing and concave down? So you have to kind of put together visually what information is provided to you based on the first and second derivative. And that's what this section in the book is all about. Now, the authors address the term antiderivative. Let me at least mention it here. And we won't do anything with it. We'll just mention it, and then we'll move on. No, actually, let's do a little bit with it. That'd be kind of stupid to just mention it. So we know if we can start with a function and take its derivative, we know what all that tells us. Now, let's suppose we start with the derivative, and we want to come up with the function. Let's do one kind of quick and easy example here. Let's go the other direction. Let's say we start with the derivative, and we want to sketch the original function. And you'll get a whole lot better at this, but I think the authors are just trying to get you to just think for a few moments in this direction. And then basically all of 241 is you thinking in this direction. So let's graph the function. So what do we need to pay attention to? Think about now, we're starting with the derivative. wouldn't you want to know where the derivative is 0?
Mm-hmm.
So I don't know what numbers those are. Let's call it left A and right A. So we come out here to negative A and positive A, whatever they are. Now the derivative is 0. What does the function have to be doing?
Flattening out.
Flat. Okay? Is that all right with everybody?
Mm-hmm.
Now what's next besides where the derivative is 0? You might want to pay attention to where the derivative is positive. Here the derivative is positive, right? And here the derivative is positive. What should the function be doing in those areas?
Increase.
Increasing. Okay? So where the derivative is positive, over here on the function, we better show that it's increasing. And down there where the derivative is negative, our picture better illustrate that the function itself is decreasing. Now the only questionable issue is where to start. And you'll see this come into play when in the latter part of this course and in most of Calc 2, is that we could start this wherever we wanted to. In fact, that's where the derivative doesn't tell us all we need to know about the function. We've got to have a point that we know it goes through. So one version, let's say that we know it has to go through the origin. I'll just hypothetically throw that in. Now I think we can sketch this function based on what the first derivative tells us. What is it doing over here to the left of A?
Increasing.
It's increasing. And what's it, I'm sorry, to the left of negative A? And then when we get to negative A, what happens?
Decrease.
It's positive, so it's increasing, right? And then it gets over here to negative A, and then the derivative is 0. Does that look like the derivative is 0? Then what does it do between negative A and positive A? Decreases, right? The derivative is negative, so the function decreases. I know it has to pick up this point. Still decreases. And what's it doing at A? Derivative is 0. Means it's flat there again. Derivative is 0. And then after that, the derivative is what? Positive, which means the function is increasing. Does that look like they could work hand in hand? If you start with the derivative, you can find its antiderivative by using the same properties that we looked at from the function to the derivative direction. Now throw them in reverse. Look at them from the derivative to the function direction. In other words, if the derivative is positive means it's increasing, it kind of goes this way as well, doesn't it? If the function's increasing, the derivative's positive, it goes both directions. Same thing with this one. Now let's say that, and this is probably something I don't need to do, maybe I shouldn't, but I kind of threw this in, that the f of 0 was 0. What if the f of 0 was 3?
You just move everything on.
Just shift it up, right? It's got to be that shape, doesn't it?
Mm-hmm.
Based on where the derivative's positive in these regions and where the derivative is negative, it has to have that shape. So what you would do is you would increase to a point up here, decrease to here, decrease to some value here, and then increase from there. So you'll see that you don't really get an answer. You get what your authors refer to as a family of curves. It's the same curve, but they might possibly be shifted. Can you think of another reason why that's true? Can I move this? Anybody? Any questions on that? Let's take a function. Without going through the long-winded definition of derivative process, If we start with the function 3x squared plus 11x minus 8, the derivative is 6x plus 11. Okay? That's a fact. I mean, if you don't trust me, go after this class and go develop it using the definition of derivative. But that is true. But if we start with that derivative, could we develop some other answers besides 3x squared plus 11x minus 8, for which 6x plus 11 is the derivative? Yeah, there's a whole bunch of different answers. This is why there's a family of functions. It's got to be 3x squared plus 11x, but it might be plus 2. It might be minus 14. It might be plus 7. So do you see how they're the same curve, just shifted up or down from one another? Because the only thing that this tells us is this. We can't tell from that what this arbitrary constant at the end might be, if in fact there is one. It might be 0. So you end up with not a single curve, but a family of curves that are the antiderivative of the given f prime of x. So you never have that problem going in this direction, but you always have that problem going in this direction. Okay, one last example. Any questions on that before I move it? Everybody all right with that? Let's say that you had a derivative. There's some method here to my madness. Let's say that your derivative graph looks like this. Could we start with this function, which, by the way, I hope looks kind of familiar, and could we develop what is its antiderivative? And we could do it the same way, couldn't we? Where this is positive, the antiderivative is increasing. Where this is 0, it's flat, that kind of thing. So we could come here to these 2 points. So here the graph has got to be flat. Down here I'm going to try to graph f of x. Here the derivative is positive, which means down here it's got to be increasing, right? Here it's positive, so it's got to be increasing. And this area right here, the derivative is negative, so the function's got to be decreasing. Now, can I offer a picture that I think does that, and that hopefully we'll be able to make a tie here between these? Derivative's got to be 0 at this point. The derivative's got to be 0 at this point. It's got to, here it's positive, so it's got to increase. Here it's negative, so this thing has to decrease. Decrease the whole way, right? And here it's positive, so this graph has got to increase. How about that? What was the first graph? Cosine. That was the derivative graph, right? What did we get for its antiderivative? Sine. So if the antiderivative of cosine is sine, what's the derivative of sine? Cosine. I told you there'd be a little method to my madness here. So there's our first look at the fact that the derivative of the sine function has a high likelihood of being another pretty simple former friend of ours, the cosine function. Now we'll be able to actually do that better with the definition of derivative, but there's our first look at that. Problems from this that you ought to take a look at, and if you have questions about these and any other questions, we can look at these tomorrow. I think this will be pretty quick and easy for you. And in fact, tomorrow, just any question that you have, any homework question, anything like that is fair game. Umair.
Like we were talking about equations, and we could find the equation of these types of equations with the integration.
Wait a second, don't pack up quite yet here.
We could find the exact formula with the integration formula.
Anything, but like when you're looking at the derivative graph,
ax
anything
plus
above, anything above.
ax squared
yeah,
plus
it's-
bx plus
it's-
c, the integration formula. Like
Yeah,
at the
well,
end
don't-
you use this c.
Yeah, don't worry too much about anti-differentiation and getting the exact solution. Right now, we'll get to that. There are certain ways that we can get a solution as opposed to a family of curves. All right, see you tomorrow.
That line right there.
That means here.
No. If you'll call me or email